Hey everyone, this lecture is on the second part of Chapter 4. As I said, Chapter 4 was pretty large. In the first part, we talked about the periodic table, we talked about how we came to the structure of the atom that we know today, and a few other things. In this lecture, we're going to talk more about electrons, energy levels, and electron configurations, just to name a few of the topics and concepts that we're going to go over. So if you have not watched Chapter 4, Part 1, stop this video and watch the Part 1, because otherwise this one will make no sense. Alrighty, put on your seatbelts. Here we go. The first topic we're going to cover is electron energy levels. And in order for you to understand those, we first have to talk about light as a wave. Electromagnetic radiation, aka light, consists of energy particles that move as waves of energy. You're going to see the terms wavelength, frequency, and energy relating to electromagnetic radiation. Wavelength, I abbreviate with a lambda. Frequency is just an F. Energy, I typically don't abbreviate, but if I do, it'll be a capital E. Let's define these. So a wavelength is just the distance from peak to peak, as is shown here, or trough to trough. So top to top, bottom to bottom. The frequency is the number, let me draw it over here, the number of cycles that can occur in 1 second. So how many wavelengths can you do in 1 second? The frequency of a wavelength is related to the energy. So if you have a high frequency, then you'll also have high energy. If you have a low frequency, then you'll also have low energy. Higher frequencies and higher energy are associated with short wavelengths. So that's depicted down here, the kind of bluish purple wave that we have. That's a short wavelength, and it has a high energy and a high frequency. Low frequency and low energy waves are long wavelengths, and that's what's shown at the top, the red wave. There's a whole spectrum of waves, and going from the longest wavelengths to the shortest wavelengths, we're going from low energy to high energy, and lower frequency to higher frequency. Some of the things that you might know are radio waves, so AM, FM, if you're listening to the radio on your way into work, or if you commute to class, if you ride in the bus or something like that, get an Uber, you might be listening to the radio. The microwave, if you heat up your food in a microwave, then you're very intimately familiar with microwaves. There's visible light, which is what we see. And then there's X-rays, which if you think about going to the doctor's office, or the emergency room if you've broken a bone, but the dentist's office where they do X-rays of your teeth every year. So there are lots of examples in everyday life that show the electromagnetic spectrum that you may not be thinking about, but you already have a reference. What you will need to know from this slide isn't necessarily the exact frequency of what a radio wave is, but you'll need to know that radio waves have a longer frequency, lower energy, and lower, Microwaves have a long wavelength, low energy, and low frequency, in comparison to, say, X-rays. So you will need to be able to compare these qualitatively. It turns out that elements also have a spectrum. If you put a gaseous element into a lamp and you heat it up, the light that is emitted when you pass it through a prism is going to separate into distinct colors. And each element has its own unique atomic spectrum. It's kind of like a fingerprint. And those distinct colors come from electrons getting excited and then releasing energy. So this brings us to electron energy levels. As I said, the lines in the atomic spectrum that are associated with each element are associated with the changes in energies of the electrons. Each electron has a specific energy known as an energy level. So you're going to see that energy level represented as N, and it will also be called the principal quantum number. I may also refer to it as the main energy level. Those are all the same thing. As you increase the energy, you're increasing the value of N. So N equals 1 versus N equals 5. N equals 5 is going to have a higher energy. This also means that the electrons are farther away from the nucleus. So the higher the N, the farther away the electrons are. I like to use the example, which is not an exact analogy, but it works pretty well, where when you're 5 years old, you're not exactly going really far away from your house, right? Certainly not without your parents. Maybe you're allowed to play outside, in front or in the back. Maybe you can play in your room without anyone directly watching you, but you're not going anywhere. You're not saying, all right, Mom, I'm picking up the keys. I'll see you tonight for dinner. Not at 5 years old, not in my house. But at 15, you may be able to walk to a friend's house and stay there for a while. Or you might be sent to go to the store or something like that. You can go a bit further away from home. So while age, we're not talking about an increase of energy, but we're talking about an increase in your age. And if you think about that in relation to the increase in the value of N, the bigger the N, the further away you can go. The last little bit of information on this slide that we're going to cover is that the energy of an electron is quantized. That means you can have specific energy values and nothing in between. So if we have N equals 1, 2, 3, and 4, there is no 3.5, there is no 1.2. Those don't exist. You're either in energy level 1 or 2. You can't be in 1.2. You're either in 2 or 3. You can't be in 3.5. There is no 3.5. This is another depiction of the energy levels, and it just groups together the fact that all the electrons in the same energy level are going to be grouped together. So you can have multiple electrons in an atom that are on the same energy level, and they share the same principal quantum number, the N. When an electron changes its energy level, it requires either absorbing energy or emitting energy. So let's say that I have N equals 1 and N equals 2. I have an electron in n equals 1. In order for it to go from n equals 1 to n equals 2, I have to add energy. That means that the electron is going to absorb energy. But let's say that electron, I'm tired of being in n equals 2. There's nothing fun up here anymore. In order for that transition to happen, we have to have energy emitted or released. That energy is in the form of a photon. So for each electron that experiences a change in electron energy level, there's going to be one photon associated with it. So if you have 1,000 electrons and they're all in n equals 1, if you want them all to go to n equals 2, then you need to add 1,000 photons of the correct energy to move all of those electrons up one energy level. Within these main energy levels, the N's, there are sublevels. So if you think about a mall, like a real indoor mall where there's different levels, you don't just go in and everything is just out there on one level. There's some separation. Each store has its own little corner somewhere. There's kiosks, there's a food court, right? So there's some kind of division among the floors in a mall. It's the same thing within these large energy levels. We have the principal energy level, which is the n equals 1 or n equals 2, and then we have sublevels. Those sublevels are S, P, D, and F. And the arrangement of the electrons in these sublevels within the main energy level determines the physical and chemical properties of an element. Each energy level, so we're talking about the n equals 1, 2, 3, etc., consists of one or more sublevels. The number of sublevels in an energy level is equal to the principal quantum number n of that energy level. So for n equals 1, there's one sublevel. For n equals 5, there are 5 sublevels. The order of the energy in terms of lowest to highest is S, P, D, and F. This is a visual representation of the types of orbitals and what you're going to see. So in n equals 1, you only have the S. In n equals 2, you have the S and you have the P. So the number of sublevels, there's 2. In n equals 3, you have S, P, and D. So you have a total of 3 sublevels. Let's talk about these different sublevels. So the S orbital, we were talking about S, P, D, and F. We're going to talk about their three-dimensional volume. The location of an electron is described in terms of probability. So you can't say this electron is exactly here. You can't give an electron a specific address, like you have a permanent address, which is most likely your parents' house, or if you have an apartment, then that's your permanent address. Electrons don't have that. What we have is more like, well, they're in this neighborhood. So maybe, or even they're in this town. This electron is in Greensboro. This other electron, is in Chapel Hill. This other one is in Ashboro. So we can't pinpoint a specific place, but we can say it's likely within this space. For the s orbital, that shape is a sphere, and it can hold a maximum of 2 electrons. As the energy level gets bigger, the size of the volume which you may find that electron gets bigger. So 1s, this is our volume here. This is our sphere. For the 3s, notice that it is bigger. We have low energy, high energy. And this is relative, of course. So the higher the energy level, the larger the space that an electron can occupy. For p orbitals, they're shaped kind of like dumbbells, or kind of like figure 8, And there are 3 of them, which can each hold a maximum of 2 electrons. So 2 times 3 gives you 6 total. So the 2px can hold 2 electrons. The 2py can hold 2. And the 2pz can hold 2. So that's a total of 6. The x, y, and z just talks about the geometry. They're all p orbitals. They're all the same energy. It's just that the orientation is a little different. The d orbitals have the d sublevels contain 5 orbitals. Each of those orbitals can hold 2 electrons. So that means the d sublevel can hold a maximum of 10 electrons. The shapes of these orbitals is a little bit funky. So 4 of them have this kind of clover leaf shape. But then the 5th one, it's kind of like a p orbital plus a donut. And that's the 5th one. It's a little special. Now there are f orbitals, but we're not talking about their geometry. You'll hear about the f orbitals later, but you do not need to know anything about their geometry or their shape. So we're talking about orbitals. We're talking about the maximum number of electrons that can fit in each orbital. Part of that has to do with the Pauli exclusion principle. And that states that each orbital can hold a maximum of 2 electrons. So within each sublevel, each orbital can hold 2. And the reason is because electrons, they're negatively charged. So if you have multiple electrons trying to hold hands and move in the same direction, they're not going to like that. If it's the same charge, like negative and negative, they're going to repel each other. So if they're going to coexist in an orbital, they have to have opposite spins. And we represent that with an arrow. So an arrow going up and an arrow going down. That shows opposite spins. This table gives an example of the maximum number of electrons that can fill each sublevel, going from energy level 1 to 4. There's more than 4 energy levels, but this just gives you an idea. So in the first energy level, there's only 1 sublevel, and that sublevel is the 1s. There's only 1 orbital, and it can hold a maximum of 2 electrons. So the total electrons within energy level 1 is 2. If we were to just look at energy level n equals 2, well, we know that since n equals 2, there's going to be 2 sublevels. In this case, we have S and P. Within those, we have one s orbital, and then there are 3 p orbitals. The maximum number of electrons that the s orbital can hold is 2. The p can hold 6 because there are 3 orbitals, and each of those can hold 2 electrons. If you total up all of the electrons in the energy level 2, so the main energy level, 6 plus 2 gives you 8. Now let's say that we had an element that had 10 electrons. That means that it would fill the 1s, the 2s, and the 2p with its electrons for a total number of 10 electrons overall. So all of this information is helping us build to where we can write electron configurations. But you first need the information on how to describe where the electrons can be in an atom. So let's do a quick learning check. Indicate the type and number of orbitals in each of the following energy sublevels or levels. N equals 1 is an energy level, right? So n equals 1 tells us that there's only going to be one type of sublevel. There's going to be the 1s, and that's it. The 3p sublevel, that's not a main energy level, it's a sublevel, right? So it's going to have 3 p orbitals, but there's only one type of orbital. The type is the p. So that's just to help you practice what some of the terminology means. It's really just a vocabulary lesson. So make sure you understand the difference between an energy level and a sublevel, and that you understand the difference between a sublevel and orbitals. With all this information, we're ready to start writing electron configurations, and we can also draw orbital diagrams to describe where electrons are in atoms. We're going to start by talking about orbital diagrams. So remember, the Pauli exclusion principle says that we can only put 2 electrons max in any orbital, and they have to have opposite spins. So we're going to have to represent our electrons with arrows, and those arrows indicate their spin. You're going to fill the orbitals and the energy levels from the lowest energy to the highest energy. And you fill them with electrons one at a time before you start pairing up electrons. So carbon has 6 electrons. And this is the finished orbital diagram. But how do we get there? Well, we know that we're going to have to fill the 1s, the 2s, and the 2p. So let's first fill the lowest energy level. That's the 1s. We can fit 2 electrons there. We're going to move up 1, and fill the 2s because that is the next lowest in energy. So now we have filled 4 slots. We still have 2 more electrons to place. Instead of placing them in the same orbital, we're going to give them some space. The electrons don't want to pair up unless they absolutely have to. Because think about it. Maybe I'm just telling on myself. When I grew up, we were not well off. So when family visited, it was you're sharing your bed, but it's a twin size bed. We'll learn. So you got one person laying regular, and then the other person you got feet next to your head, okay? That's just the way it is. Who wants to do that on purpose? Electrons don't, and you probably don't either. I didn't. Love you, cousin. But for real, your feet stink. You've been in the car for 12 hours to travel to come see us. You didn't think to take a shower and clean between those toes? That's not fair. So think about that when you think about doing these orbital diagrams. You don't want somebody's stinky feet near your head. So don't pair electrons up unless you have to. I know I'm a little bit crazy, and that may not be for everybody, but I can't change who I am. I apologize. Not really, though. It's just, it is what it is. Anyway, let's do another example. Nitrogen atoms are found in amino acids, proteins, and nucleic acids. Draw the orbital diagram for nitrogen. Immediately, what do you see that's missing? You're not told how many electrons to place. You have to rely on the beginning of chapter 4 to figure that out. So you're going to pull out your periodic table and you're going to find nitrogen. Its symbol is a capital N. When you do that, you're going to find the atomic number for nitrogen. Its atomic number is 7, which means that there are 7 protons in the nucleus of a nitrogen atom. Now, why are we talking about protons when we're supposed to be writing an orbital diagram for electrons? In a neutral atom, the number of protons is equal to the number of electrons. So if you have 7 protons, you're going to have 7 electrons. And now you're ready to draw a diagram. So we start by filling the lowest energy first. That's the 1s. See what I did there? That's not right. You don't want to have them both going in the same direction. So opposite spins for electrons. The next energy level that we're going to fill the energy level 2. We're going to start with the 2s. Put another 2 electrons. We've placed 4 electrons. We still need to place another 3. You can give them their own space and put them into their own little orbitals. And that means that we've placed all 7. So you want to double check and make sure that you're not pairing up electrons without cause. So if we had one more electron, if we were doing oxygen, let's say, which has 8 electrons, then we would absolutely have to add another electron here like this. But we don't. Just keep in mind, don't double up unless you have to. To go along with those orbital diagrams, we also have to talk about electron configurations. So this notation is used to indicate the placement of electrons in an atom. You're showing how the electrons are filling the energy levels and the sublevels, and that goes in the order of increasing energy. There's what's called the full notation, which I'll introduce first. And it's kind of the longhand, kind of like doing long division. Then there's also the abbreviated form, which uses a noble gas to represent all the electrons preceding it. So I'll show you both, but we're going to start with the full notation. Now, as I said, there's an order to how the electrons will fill the energy levels and sublevels. What I'm about to write is going to be the order all the way through, so you can write the electron configuration for the largest element on the periodic table. I will also include the maximum number of electrons that each sublevel can hold. So here we go. You always start with the 1s. S orbitals can hold 2 electrons. So that superscript there tells you the number of electrons in that particular sublevel. We move on to fill the 2s, again with 2 electrons. Then you fill the 2p, which has 3 orbitals, which can each hold 2 electrons. That means that you can hold 6 electrons in each p sublevel. We move on to energy level 3. You fill the s with 2 electrons and the p with 6 electrons, followed by the 4s with 2 electrons. Watch this part. We're going to dip back into the energy level 3 and fill the 3d. The 3d is slightly higher in energy than the 4s. But don't worry, we're going to be able to write this out and you'll be able to see it on the periodic table and it will help make sense. So you're going to want this that I'm writing in your notebook, but you're also going to want to have a printed periodic table that you can mark up with color pencils or markers or whatever you have, so that you can mark it up the way that I do in the coming slides. So we filled our 3d10. The next thing you're going to fill is the 4p, and the p can hold another 6 electrons. We've just covered all of the elements through the 4th period on the periodic table. Now we're on the 5th period. It's going to repeat in a similar way. You fill the 5s, then you fill the 4d, then you fill the 5p. The 6th period is a little bit different still. So we fill the s, which is normal. Then we're going to bring out these f orbitals. We didn't talk about the shape of the f, but they exist. And I'll show you where they are, where the elements are that fill the f orbitals on the periodic table. There are 7 orbitals in the f, which means they can hold a total of 14 electrons. So for row 6 and row 7, you're going to fill the s, then the f, then you fill the d, and then you fill the p. The 7th row is a repeat. 7s, 5f, 6d, so close, y'all, then 7p. This is the full order of how the electron sublevels and levels are filled, all the way from the lowest energy to the highest energy. Again, make sure you have this in your notebook. This tells you the maximum number of electrons in each sublevel. So if you have an element that doesn't have a complete 3D, that's okay, You don't have to write 3d10. Maybe there's only 7 electrons in the 3D. That's totally fine. From here, we're going to write all over a periodic table. Okay? So all of that information, I'm going to help you visualize on a periodic table. You may want to do this along with me, or you may want to print something out and do it on your own time after you watch the video. But please, please, please do print out a periodic table, or if you have a tablet or a phone that allows you to do this, or if you have a touchscreen laptop, make sure that you make a copy of the periodic table that I'm about to make right now. You will be mad if you don't. I'm going to color code, and feel free to be inventive as long as you label it properly. So what we have in black is called the S block. All of the elements here are filling the S orbital. Next, we're going to label our P block, which is on the right-hand side of the periodic table. These elements are filling their p orbital. The elements in the middle of the table, these are your transition elements. This is the D block. They're filling the d orbital. And last but not least, below the main periodic table, we have the F block. Notice there's an asterisk here and an asterisk here. That means after barium, you need to jump down here to the F block. And notice barium has an atomic number of 56. Lanthanum has an atomic number of 57. We're not just skipping from 56 to 72. You have to go down to the F block. Now I'm going to go through and write the different energy levels. So this is your N equals 1, 2, 3, 4, 5, 6, and 7. So this would be your 1s, 2s, 3s, and so on. We can do the same thing with all the other blocks. So notice the 3D is in the 4th period. So you don't have to necessarily memorize that. If you can recreate this chart, then you can just see it. We're over in the P's. And then finally, I'll fill in the F. So these are the different blocks. They're filling the S, D, P, and F orbitals. And I've also put the sublevels. So you've got the main energy levels over here, and then you've got the different sublevels for each row. This will help you tremendously as you're learning to write the full electron configuration. As you get more comfortable, you may not need to have all of these notations on your periodic table. We'll talk about the steps for writing an electron configuration, but I feel that it is much better if we go through a couple of examples. So the first thing you're going to want to do is locate the element on your periodic table. Then you're going to walk across each row of the periodic table until you get to the element that you want, right? Once you get to that row, you're going to count the number of electrons that's going to occupy that last sublevel block. And that'll make sense in just a moment. Let's say that we wanted to write an electron configuration for chlorine. The first thing you have to do is find it. So chlorine is over here in our P block. To be more specific, our last sublevel for our electron configuration should be 3p, because that's where chlorine is. I'm going to fill in the other parts of the periodic table so that you can see how you can walk through it. Trying to stick with my color coding here. So let's start writing. You always start with 1s. We're going to put 2 electrons in the 1s. And by the way, you should always know how many electrons you need. We need 17 for chlorine. I like to keep a tally along the way, and I recommend that you do that until you feel comfortable. Again, this superscript here tells you the number of electrons in each sublevel. So in the 1s, we're placing 2 electrons. So in your tally, you can write that. After that, you have to go down to the second row or the second period. Now we're in the 2s. We haven't reached chlorine yet, so we know we're going to fill it up. The s can only hold 2 electrons, so that's what we do. So we've placed a total of 4 electrons. That means that we have 13 left. So you move to the P block, still in row 2 or period 2, and we're going to fill that all the way up. We can hold a total number of 6 here. And look, 1, 2, 3, 4, 5, 6. There are 6 elements in the P block. So that tells you there can only be 6 electrons here. If we add another 6, that gives us a total of 10 electrons. So we're not quite there yet. Now we start filling the main energy level 3. You start with the 3s. We're not at chlorine yet, so we just fill it up. Now we're at 12 electrons. We're getting close. Now we're in the P block, and we know that's where chlorine lives. So we're going to write 3p, and then we're going to count 1, 2, 3, 4, 5. So we only need an additional 5 electrons to complete our configuration. You can always add up those superscripts to make sure that you place the right number of electrons. And this is our electron configuration for chlorine. That's the full one. There's an abbreviated version, which will take a lot less time to write. Chlorine is in the 3rd period. if we look at the noble gas in the period above, which remember, these are our noble gases, and that's something you should know from the common group names from the chapter 4 part 1 lecture. So if you don't remember that, shake your brain out and try to put it back in there, okay? So the noble gases are this last column here. We're going to look at the noble gas in the row above the one your element is in. We care about chlorine. It's in period 3. So we are going to start our abbreviated electron configuration using the noble gas from period 2. That is neon. And neon pretty much says all of this. So what I just underlined, 1s2, 2s2, 2p6, because that's the configuration for neon. And what we're saying here is chlorine has everything that neon has, plus this other stuff. Hopefully the colors will help you. So we took the noble gas from the period above chlorine, and then we added on what was in the same row. So those remaining electrons we have to place. This chart gives you examples of orbital diagrams and configurations for S block and P block elements, so 2s and 2p. You can use this as a reference to make sure that you're writing it kind of in the right format, and especially for the orbital diagrams, for making sure that you're doing your electrons correctly and you're not pairing them without due cause. For configurations in period 4 and above, remember that I wrote out that long configuration for the full electron configuration. This is where some of those things come into play again. So I'll remind you again. In the 4s sublevel, you're going to fill that before you fill the 3D. And the same thing is true. You're going to fill the 5s before the 4D and the 6s before the 5D. So let's write a stupidly long electron configuration for neodymium. Neodymium is all the way down there. It is in the F block. So get ready. Make sure your pencil is sharp because we're going to be writing for a while. Then you'll probably have a much better appreciation for the abbreviated form. I'm not going to rewrite all of those decorations for the periodic table, but I will label the blocks. I'll also write the period number. So those are the period numbers. And then we just have to remember the the special exclusions. So I'll write one there and one there so that we keep it in mind as we're writing. the best place to start is the beginning. So we're going to start with the 1s. Now, neodymium has an atomic number of 60, which means it has 60 electrons. I'm not going to do the tally, but you can do it along with and double check, because sometimes I make mistakes. Pretty confident about this one, but you never know. So we're going to fill the 1s with 2 electrons. We're not even going to stop and think about how many more we need to go. We're not even in the same row, so we're not even in the same country as neodymium right now. We're going to go on down to the second row. We're going to fill our 2s, then hop across to the 2p and fill that. Nowhere near neodymium, so don't worry. We're going to fill the 3s, go across, we're in the 3p, and fill that. Now we're in period 4. This is where you need to pay attention. We fill the 4s, then we fill the 3d. Then we fill the 4p. And it's the same pattern for the 5th row. We fill the 5s all the way. We fill the 4d all the way. Then we fill the 5p. We are now in neodymium's neighborhood. So let's slow down. We're in the S block, period 6. You always fill the S first. Then we get to the asterisk, which tells us to go down to the F block underneath the main periodic table. Now we're on the same block as neodymium. We're filling the 4F, and you count 1, 2, 3, 4. That is the full electron configuration for neodymium. Let's write the noble gas, or the abbreviated configuration. You might be mad at how much quicker it is, but believe me, you need to understand the full electron configuration before you can appreciate and understand what the abbreviated form really means. We are in row 6. Just like in the last example, we need to look at the noble gas in the previous row. So that means we're looking at xenon. And xenon accounts for everything up to here. Then you just figure out what you have remaining. Xenon has 54 electrons. Neodymium has 60. So you have 6 more electrons to place. We're starting in the 6th period. So we fill our 6s with 2 electrons. Then we travel down to the F block, count, and put 4 electrons in the 4F. That's the abbreviated version. But to understand what this means, the xenon in brackets, you have to understand the full electron configuration. We'll do more examples of this in class. It's one of those concepts that you just need to practice over and over again and use the visualization. So I'll take this time to mention that there is a video in the Chapter 4 folder for electron configurations. I found it on YouTube. This person does a really good job of visualizing the full and the abbreviated form. I think she calls it condensed or noble gas. Same thing. It's about 7.5 minutes long. And if you are a very visual person and this just wasn't hitting exactly right, you need some more help, watch that video. So that link is already in the chapter 4 folder. As with everything, there are some exceptions. There are times when electrons will move to the 3D versus the 4s, even though the 4s is not full. And that's simply because of stability. So chromium will move one of its 4s electrons to the 3D so that the 3D can be half filled. And that's more stable than having 2 electrons in the 4s and then only 4 electrons in the 3D. The same thing for copper. Copper will complete its 3D sublevel and leave the 4s open. So there's one slot in the 4s. But these are just exceptions to the rule. This is a table that has examples of electron configurations for elements that are in period 4 and above. And notice the exceptions that I noted on the other slide are on this slide too. The last part of chapter 4 talks about trends in periodic properties. So we're going to talk about valence electrons, atomic size, ionization energy, and metallic character. Those are the things that you're going to need to understand and know the trends for just by looking at the periodic table. This is another place where you're going to want to have a periodic table that you can draw on. You probably don't want to do it on the same one that you put all of the S block, P block, and stuff on for the electron configurations, because it's just going to be too busy. So print out another one. So pause, go print or something. And you're going to want to write these trends in with the arrows for when something's increasing or decreasing. So for valence electrons, we call it a trend, but we're not saying that something is necessarily increasing or decreasing as you go up or down a group. But as you go across the periodic table, the number of valence electrons increases. So you can draw something like this. On your periodic table. Now we're only talking about the representative elements, and those are the ones that have the A that come after them. So that's the far left and the far right. We're not talking about the D block or the F block. We're talking about S block and the P block. Those are the representative elements. The valence electrons are the electrons in the outermost energy level. So if you have an element that is in energy level 3 and it has electrons in the 3s and the 3p, those electrons are going to be the valence electrons. An easy way to know is by looking at the group number. And again, you're going to want to look at the number that has the A after it, because we're only talking about the representative elements. So that group number gives the number of valence electrons for that particular group. So if you're looking at group 5A, then there are 5 valence electrons. That's simple. So let's use the periodic table to write the group number, period, and valence electron configuration for calcium. First thing you got to do is find it. So calcium is in the S block, and it's in period 1, 2, 3, 4. So we should have 4s something as our valence electron configuration. We know that just from where it is. Now your periodic table should have all of these groups labeled. And all you have to do is look at the number that's in front of the A. So that means that the group number is 2A. The period is 4 because it's the fourth row. And the valence electron configuration well, we're in the row 4, so that's period 4 and energy level 4. And we have 1, 2 electrons in the S block. So it's 4s2 for the valence electron configuration. Again, we'll do practice for this in class. This is a table for representative elements in periods 1 to 4. It tells you how many electrons total, which is this number here up top, which is also the same as the atomic number. And then below, you see the valence electron configuration. Notice that in each group, it's always something and then S1. Something S1. So this is a visualization of how each group has the same number of valence electrons. We can represent those valence electrons as dots on something called a Lewis symbol. You're going to take the symbol for the element and literally draw dots around it to represent electrons. Let's say that we had sodium. Sodium is in the S block. And if we go back, you can see it's in group 1A. That means it's going to have 1 valence electron. Anytime the number of valence electrons is 1 to 4, you just arrange the electrons as a single dot. So you can put a single dot there, or there, there, or there. Same thing. There's 1 electron. That's what you're showing. But let's say that we had something from group 7A, like chlorine. That means that you have 7 valence electrons. So you're going to write the symbol for chlorine, and then you place them. That's only 4. So you have to pair up until you get to 7. So this would be an acceptable Lewis symbol for chlorine. And of course, I'm ahead of myself. I just wrote the electron dot symbol for chlorine. But again, we'll show it this way. That's the same thing. As long as you have 1 unpaired electron and all the others are paired, then you have 7 valence electrons. The next trend we're going to cover is atomic size. So this is talking about the size of the atom. As you go from the top of a group down to the bottom, the atomic size increases. You're going to want to draw this. And you may want to use a different color for the different trends. So we have atomic size, and then we're going to have another 2 that you're going to want to draw arrows for. As you go left to right across a period, you're going to decrease. Now, let's take a second to explain that. As you're going down the periodic table, your N is increasing, right? So that means that the size of the orbitals is getting bigger. So your 3s orbital is much bigger than your 1s orbital. So your electrons are going to be much further away. It follows that as you increase your energy level and the electrons are able to be further away from the nucleus, that means your atom size is going to get bigger. But across the periodic table, we're not increasing the energy level, but we are adding protons. And those protons are going to draw in the electrons a little bit closer to the nucleus. Because remember, opposite charges attract. So as you go across a period, the atomic size is going to decrease. Let's talk about ionization energy, because that is related to atomic size. Ionization energy is the energy required to remove one of the outermost electrons. And remember, that's another way of saying valence electrons. So if we use sodium as an example, the valence electrons that we're interested in are here. There's only one. The amount of energy that it takes to remove that electron is the ionization energy. As the distance from the nucleus to the valence electrons increases, you're going to have a decrease in ionization energy. So let's draw that. That dot's supposed to be in the middle. Let's try that again. I'm not an artist, just a scientist trying to be an artist. Let's say that this is energy level 1s and this is 4s. Look at the radius of the circle for the 1s. It's pretty small. So that means that the electron is closer to the nucleus. So it's going to be attracted a little bit more. Whereas the electrons here that are the outermost electrons, remember, that's what we're talking about. This electron is going to be farther away. So it's not going to have as strong of an association to the nucleus because it's just not as close. So it's going to be able to be picked off a lot easier. In general, ionization energy is low for metals and high for the nonmetals. So on your periodic table, you're going to want to write the arrows as you go down a group, ionization energy decreases. As you go across a period, ionization energy increases. And you'll see here a figure that is much better drawn, but it doesn't have the passion that I have. The final trend that we're going to cover is metallic character. An element with metallic character is one that loses valence electrons easily. So it would make sense that as you go down, you're going to have an increase in metallic character, because the ionization energy decreases. Low ionization energy is the same thing as saying high metallic character. As you go across a period, you're going to have a decrease. Remember, we said that ionization energy is generally low for metals and high for nonmetals. As you go across the periodic table, you're getting closer and closer to the nonmetals. So your metallic character is going to decrease as you approach things that are not metals. It makes sense, I promise. This table summarizes all of the trends that we just covered. So it's a great way to double check everything. It's all in words. And if you want to have this in your notebook too, you can. But I highly recommend that you have a periodic table that's decorated with the trends, and it has the arrows for increase and decrease and all of that for each of the different trends. Try to use a different color so that you're not confused. For me, using different colors and things will help trends and stuff kind of stand out more. So if you don't have color pencils or markers or anything like that, if you're able to, go to the Dollar Tree. Like seriously, go to the dollar store, spend $1 and some change, and get some color markers if you can, because it will really help you with this chapter. The last slide for each of these chapters is going to be a concept map. This concept map, I'm not going to go through it all, but it will help you place some of the vocabulary words that we've gone over the course of the whole chapter, and place things into context and show how they're related to each other. So if that kind of thing helps you, go through this concept map and make sure that you understand the relationships between all of the different topics that we covered in chapter 4. It's a really big chapter. So you do want to take some time to make sure that you understand not just the individual concepts, but how they all link up together. Finally, a few quick reminders. You're going to have your chapter 4 check-in part 2 and your Mastering Chemistry homework and quiz due on Sunday. So I hope that you have taken to heart what I said. Start the chapter 4 homework early. Do the stuff related to what we covered in class already, so that next week you're not trying to scramble. Our next exam is going to be coming up in early October, and it's going to cover chapters 4, 5, and 6. So be on the lookout for that. Obviously, we're going to cover everything before you get the exam. So make sure you keep up with your homework. Make sure you keep up with the lectures, because we are moving fast. If you need any extra help, or you just want to say hi, you can always shoot me a message using course messages in Blackboard, and you can set up a time to meet with me. I'll be posting shortly about when office hours will be permanently for the rest of the semester. So look for that announcement soon. Have a good one. I'll see you in class.